Hey kids, let's do some reviewing of sketching graphs. So we are almost at the end of Unit 3A. So we've touched on this idea before of what does a graph of derivative look like compared to the graph of its original. But we want to make sure to review a couple of things about that before we go into the last topic. So be careful of a problem like this. And this handout is available on our files so that you can go along with it. But again, when I highlighted in the last videos and in live sessions, please, please, please pay attention to which graph you're looking at and what they're asking you about. So they're giving me a function here, graphed. It's a regular function. It's not a derivative. So they're giving me the original, and they want me to arrange the following in decreasing order. Pay attention. Decreasing order. So least to greatest. Notice, though, that except for the number 0, all of the other ones, and it is a little hard to read, all the other ones are derivatives. If I asked you something like this on a test, I would also write the words. I would write something like, for the function graphed at the right, arrange the following derivative values, or I would just make it, this would just be a better Word document. All right, so firstly I have 0. So 0 is the great divide between the negatives and the positives, right? So when I'm looking at those derivative values, I need to think I'm going to put 0 here, and over here, I'm going to put any negative derivatives. And over here, I'm going to put any positive derivatives that I see. And again, derivatives go with the S word. Right? So what I have here, the slope at -3. So let's go to -3. 1, 2, 3, -3, and go up to the function and draw a tangent line. That tangent line is positive, so I'm going to put it over here. How about f prime at 0? That slope is negative, so I'm going to put it over here. So I've done this one. I certainly wrote down 0, did this one, this one. How about f prime at 2? So at 2, I have another negative. Can you do algebra 1, though? What's true about negative slope, the negative slope at 0 and the negative slope at 2? They're both negative, but f prime of 0 is steeper, isn't it? So f prime at 2 is still negative, but closer to 0. Like, for instance, let's say this slope was approximately -3, and this slope was approximately -1/3. Now let's look at f prime at 4. Whoa. That's still negative, but it's super negative, right? It's even steeper. So let's say that slope is approximately -10. So still negative, so I'm still to the left of 0, but I'm even more steeper. Okay, so this is a nice test question because it really does get to the concept to make sure students understand the concept of which graph they're reading, original or derivative. And it gets to approximating tangents from a graph, right? Which is what allows you to organize these values from least to greatest, right? So you double check yourself. F prime was approximately -10. F prime of 4. F prime of 0 was approximately -3. f prime of 2 is approximately negative a third. Then I had 0, and then I had the only positive slope, f prime at negative 3. All right, let's go to 2. So 2 match the graph of the originals in lowercase. So these are all the originals with the graph of the derivative. Here. So this is where you think about your handy dandy tangent line maker. Right? If I were to draw a tangent line at this point, this point, this point, and this point, because this piece of the graph is linear, you already know by power down that the derivative should be a constant, right? Constantly positive. Which graphs over here have a constant graph that is positive? Derivative is constant and positive. And then notice if you start going here, what if I drew a tangent line here, 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 and here? Well, the original function is constant, and the slopes on a constant function are all 0. Slopes 0. But the most important thing for you to recognize is to what is going on here. That is a corner. The slopes from the left do not equal the slopes from the right. So, since your derivative is a limit of slopes and the limit of the slopes from the left do not match the limit of the slopes from the left, this graph does not have a derivative at this x value, whatever x value this is. So look at the derivative graph. The derivative graph is undefined there. Crazy, right? So if your original graph has a discontinuity, your derivative will have a discontinuity. But remember, continuity does not guarantee differentiability. Therefore, you can have a continuous graph whose derivative graph is not continuous. Continuity does not guarantee differentiability. If you are continuous does not mean you are differentiable at every x, and therefore, and in this case, we weren't differentiable. We had a corner, so our derivative graph was broken. Okay. However, notice that if you do have differentiability, though, every one of these graphs over here that is continuous, meaning that a derivative does exist everywhere, differentiability does guarantee continuity. You will never be asked to write that out, but you will be given a problem where you are told in the directions that your original function is differentiable. And you are going to need the fact that your function is continuity for instance, the intermediate value theorem. And the problem doesn't say that the function is continuous, but it says it's differentiable, and you need to know that means you have continuity. All right, let's go down the line here. Lowercase b, if you were to draw tangent lines here, 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 and here, right? That function is linear. So you know that the derivative must be constant, and it's constantly negative. But look what this graph has all over the freaking place, right? A corner, a corner, a corner, a corner, a corner, right? At every one of those x values, the derivative cannot be defined because the derivative from the left is constantly negative. Let's pretend it's -1. And the derivative on the right is constantly +1, constantly -1, constantly +1, constantly -1, constantly +1. Which one of the graphs over on the right matches that? Got to write the answer there. F. Everywhere my original function is not differentiable, my derivative graph is broken. Derivative broken means original might also be broken, but it is either broken or not differentiable. And you know from a previous lesson the things that cause non-differentiability: corners, cusps, vertical tangents, and of course discontinuity. C is smooth. So little c is a nice smooth graph. So you are not expecting a nice smooth graph is differentiable. So its derivative graph should be continuous. So let's think about our tangent lines. At the left, I have a tangent line that is either 0 or very close to 0. In the middle, I have a tangent line that is 0. At the end, I have a tangent line that is also close to 0. So I'm looking for a derivative graph that starts at 0 or close to 0 and ends the same way and has an x-intercept in the middle. Can you see which one that is? Yeah, I can already tell, right? Now let's go verify some things that are going on. Slopes start at 0, and then these tangent lines increase, but then they start to decrease again towards 0. And look at what the derivative graph does. Starts at 0, increases, turns around, and starts to go back to 0. That's what the tangent lines are doing. Notice everywhere where I was just drawing tangent lines on the original, where that graph is increasing, its derivative is above the x-axis. Where the derivative is the original is decreasing, the derivative is under the x-axis. Where the derivative changed from positive to negative, the original changed from increasing to decreasing. Notice the slopes right past the slope of 0 here are negative, getting more negative, more negative, more negative, and then at the point of inflection, start to come back to positives. All right, let's go in opposite order here. Let's start with F and go up. F is a little semicircle. Look what's happening. Slopes are almost freaking vertical there. And then are positive, but decreasing till a slope of 0. Then slopes are negative and getting way, 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 way negative. So you're looking for a derivative that starts out positive because the original is decreasing, and then the original turns around and decreases. So you're looking for a derivative that is above and then below the x-axis. So B was above and below, but look at the difference between these two graphs. Both of them were increasing to decreasing, but this graph had curvature here where the slopes were increasing and then the slopes changed to decreasing. Here, the slopes are always decreasing to 0, and then they decrease, the slopes decrease. So slopes start out high and decrease the entire time until they hit 0. And then slopes decrease and keep decreasing. So where the slopes are positive and then change to negative, the original was increasing and changes to decreasing. Look at E. Again, start at the far left. I'm looking for slopes that start at 0 and kind of end at 0. That was very similar to what happened over here in graph C, right? Slopes started at 0 and ended at 0. But what's different here? The slopes are increasing to 0. Then the tangent lines I'm drawing are still positive, but decreasing. So I never had a negative slope. So no negative slope, right? This graph is always increasing. So you should be looking for a graph, a derivative graph that is always positive. Here you go. Slopes start close to 0. Right? My slopes start close to 0 and are increasing. Slopes are increasing. Slopes are still positive, but they're decreasing. But the slopes were always positive for a graph that was always increasing. So notice, since my slopes never changed signs, I did not change from positive to negative, positive to negative. My slopes were always positive. My original graph had no turning points. Right? Pretty cool. But notice at the point of inflection where the slopes changed from increasing to decreasing. When the slopes went from increasing to decreasing, my original had a point of inflection. Crazy, whack, funky. I forgot to put my answers here next to this, right? What was F? F was capital E, and E was capital E. Oh, no, it wasn't. E was A. So by default, I already know what D is, right? But let's take a look at it, right? We already know this is graph C by the process of elimination, but does it make sense? Notice that C is broken at 0. The derivative graph is not continuous. right? It's broken. If the derivative graph is undefined, the original graph is either also undefined or is not differentiable. What's going on at 0 here, right? I've got that cusp. What's happening with my slopes? My slopes start off negative, but not that negative, right? Kind of close to 0. Then the slopes get way negative very quickly, and as a matter of fact, get really, really, really close to being vertical, but not quite. Slopes negative. Slopes starting off to 0 and getting very, very close to a vertical line that is undefined. The slope is numerically undefined. And then as soon as you jump across the cusp, what happens to the tangent lines? They are immediately what? Positive, but very high. Isn't that what that graph says? And then the slopes stay positive, but come down close to 0. Now, here's a really, really, really important part. So I hope I'm not on 3 or 10 speed or whatever. This is super important. The slopes were negative. Then the slopes were positive. My graph was decreasing because my slopes were negative and increasing because my slopes were positive. There is a turning point here. It is not a nice smooth turning point. This is a smooth turning point where your derivative is equal to 0. This is not a smooth turning point, but it is still a turning point. So it's not that the derivative has to equal 0 in order to have a turning point. The derivative has to equal 0 or be undefined. And what really makes the turning point is that the derivative changed sign. A derivative changing sign. My derivative was negative, and then it changed to positive. When a derivative changes sign, the original changes direction, unless the original is itself undefined, right? So that's going to be something that, right, foreshadowing. If your derivative changes sign, then the original has a turning point. I don't know why my pen is reacting so slow. This is super important. Now, for the derivative to change sign, right, the great divide between the positives and the negatives is a derivative equaling 0, right? Here, the slope was 0. So you look at the graph, and the graph of the derivative has an x-intercept. Slope was 0. But as we just saw, the slope might be undefined, and you also have a turning point, just not a nice smooth one. You could have a corner or a cusp. Notice up here in D, the slope was positive, and then the slope was 0. So I don't have, that's not really a turning point, right? I didn't turn around. But what if my graph had looked like this? What if I'd had an absolute value graph upside down? The slopes, right? The slopes are negative. I'm sorry, the slopes are positive, the slopes are negative. I definitely have a turning point but the derivative is not defined there. All right, that's it for this video. In class, we will do some more graphs like this where you get to, on your own, work with a handout where I ask you to go the other way, right? Where I give you the graph of the derivative and ask you to match the original. And we'll also visit a website where we can do this with an applet that lets you kind of like try to match the derivative in its original. All right, I'll see you then.